Hi everyone, this is Team Apollo. I'm Pan. My team members are Miss, Xiaoxu, and Yuehui. Today we are going to talk about motion planning and control in autonomous parking. The problem we'd like to solve is to reduce the gap between the simulation and the real world. This gap is obvious in motion planning and control part. For example, it's easy to generate waypoints from point A to point B using A-star algorithm and control the car to follow the waypoints using a PID controller. But when we apply this simulation directly to GEM, the car would be out of control. That's because the paths may contain some sharp angles, and the controller, which is perfect in the simulation, may be unsuitable for the real car. So the error may become very large in a very short time. Then the system will be unstable. This is a problem we want to solve. We would like to come up with an idea to control a real car following a more smooth trajectory with smaller errors. Okay, here are the methods we use. First, the motion planning part. We use the RRT-star algorithm to get a sequence of waypoints from the start position to the end position. For the steering function, which is one of the most important steps in the RRT-star algorithm, we implement a two-stages Dubins reachability tree to check which of the sampling nodes can be reached. If a node is reachable, we conserve it. If not, we ignore it. Also, we calculate the curvature based on the GEM model and apply the value we compute in the Dubins reachability tree. The second is a controller. We use a PID controller in the real car in order to track the constant input command with zero steady-state errors and improve the stability of the system. We test different gains to get the best performance.
Next, we implemented Dubins RRT-star to take care of the non-holonomic constraints of the vehicle. The inputs to the algorithm were the start point, the end point, and the map, and the outputs being x, y, and heading position, which the controller can directly take the values from. But the one problem with Dubins RRT-star is that it does not guarantee completeness. But similar to RRT-star, it guarantees asymptotic optimality, which we learned in class. And this is because of the rewiring step. This algorithm was further tested with different obstacles for a given start and end point, and it was successful in finding the path every time. The following two figures show the implementation of the algorithm for 500 nodes. Further, we tested our algorithm for different number of nodes. We observed the optimality behavior of RRT star, which means that as the number of nodes increased, the length of path decreased, reaching the most optimal one. The first figure shows path found by 100 nodes, second figure shows the path found by 300 nodes, and finally the third figure shows the path found with 500 nodes, and this path found is the most optimal one. Here is our Dubins RRT star in action. The video shows the ROS window, which has the camera view, the LiDAR window, and the path to be followed by the controller on the top right. Once the controller is turned on, we can see the control inputs at every time step in the terminal, which is at the bottom right. In this part, you can see the outside perspective of the car following the path found by Dubins RRT star. And on the right top, you can have a look at how GEM is autonomously maneuvering to reach to the parking spot from any random position. For the last part, we would like to talk about some experiences of this class. I have had access to a broad range of knowledge starting from safety verification, perception, localization, planning, and controls. And finally, I was able to combine different modules together to form a complete autonomous system. And working on GEM was the most exciting part of this class.
PCE 484, Principles of Safe Autonomy, is my favorite class this semester. I went through every module of an autonomous car and implemented what I learned to a real car. It's a very exciting time for me, and I would like to go into self-driving area in the future. So thanks a lot for the efforts of Professor Mitra and RTAs. That's all. Thank you for watching.